Hello Internet! In this video we are going to be working on expanding our Bezier Curves. I think that's how you pronounce it. I said that last time and now I'm pronouncing it differently. This is going well. So currently we only support 3 points. So I have this line renderer set up. There's 4 points because that's what we're going to be adding next. But currently it only supports the first 3. And so this is sort of how it works. We can dynamically edit our line renders. So it actually changes in real time. And we get all this goodness. So what we're going to do is be adding a 4th point. Now the way this works is each point on this line is calculated by moving 2 points along each of these lines. So this green and this blue line. We move that point forward towards along its axis, so from down there up to here, and then from the top down to the bottom for the blue line, we move those as we interpolate across, which creates these lines which are connecting those 2 calculated points. And then that gets us a point on this curve. So what we're going to be doing is, for the 4th one, we literally are going to add a 4th point, do the same interpolation, which is going to give us a 3-point Bezier curve, and then we're going to go down and just solve it the same way. So theoretically, this can be abstracted. We can just it just goes n points. So if you have n, it should just go down until you get 3, and then you can solve it the normal way. I think. I'm not super familiar on the tech on this, but that should work. And if it doesn't, then, well, this is going to be an even more interesting video. So here is how our Bezier curve works. We are going to, I think, now that I think about it, am I going to regret doing this? Yes. Let's do 0.4 here. But I'm going to write this in a way that it can be abstracted later, so we can actually support any number of points over 3. So if you want to add a bunch of points and get some fancy line, that will work. I'm not really sure it makes much sense over 4. You kind of would get, I guess you could do like a spline, but there's other ways to do that. But definitely for up to 4 points, it makes sense. We'll keep it at just 4 for now, I think. So, what is this doing? This is calculating for 3 points. So, given 3 points, it gives us a position. This position. So we calculate the tangents between all 3 points, and then do all of that. Okay. So, we are going to take this and move this bit. Do I want to do it like this? No. No, I don't. We're going to not comment it. We are going to extract it into a new method that is going to say build Bezier curve. So this is going to actually build the curve from the 3 points defined. And so we need oh shoot, I don't want to do this. Sorry, getting ahead of myself. We want to get a point out of this. So this makes more sense. We want to pull it out here and then return the point that we calculated. And so this way, we can plug in our newly calculated points into this. So actually, do I want a ratio? Oh, first let's rename this to something. Calculate the point? Sure. So this is going to calculate a point given a ratio and a set of 3 other positions. Is that what I want? I think I'm getting to the point where it's like, oh, we could do this in a different way. But I don't know if I want to yet. Yeah, sorry. Getting distracted, but this will work way better. So, I'm probably should have considered this a bit in the, before starting this video, but, figure it out as we go. So let's create some params, which is going to be our vector3 array of the points. This is going to be a recursive algorithm. And so how this is going to work is, given a certain number of points, we're going to calculate another set of points, and then another set of points, and then another set of points, and another set of points, until we get down to 2? Actually, no, we can just do it until we get down to 1. That'll be easy. And so this can actually just return a single point, which is going to be this Bezier point, which is the result. So if our points dot length is equal to 1, then we'll return the points 0. And so effectively this is going to recursively regenerate this points list every single time, but it's going to regenerate it based off of the ratio. So it's going to take, say, 0.0 and 0.1, and then lerp between them with the ratio to add a new point, and then do that. So each time we're going to be subtracting a point off of this list, and that should get us the ability to support any number of points as long as we have 1. So if we have 1, it'll just be a point in space. If we had 2, it'll be a straight line. And then as we add more, it's going to continue to do more and more interesting things. Theoretically, this should allow us to do any sort of curves we want, and it should do all sorts of fun things. Oh man, I wish my camera was doing, because I was doing weird hand gestures during that for no reason. I guess my wall got to see them. So, for this, we have tangent lines that are calculated. So this is our exit condition. When you're doing recursive definitions, you always want an exit condition. That should be the first thing. If you don't have that, there's a pretty good possibility that your recursive definition is never going to exit. And so the next thing we want is going to be a list of vector 3s. May want it to be a linked list, but actually we're going to be converting it back to an array when we pass it into the points argument. So let's make this enumerable. Sorry, I did not really plan this. I was just kind of like, we should do this. This would be fun. So that's what we did. I can't get the next one. Aw. Yeah, I can. Don't lie to me, game. System link. Link is my new best friend, because we're going to do a count now. As long as there's one element, or if there's more than one element, we don't want to do this. But this should get us everything we need. So I can take the points, and actually I can just call first, and that will return the first element, and that should be good. So now we can make this a linked list. So linked lists are going to handle inserts a little bit better, and since we're going to be inserting things continuously, it just makes more sense to me. We'll call them the sub points. So that'll be the new linked list, like that. And then we're going to want to store our initial vector, which is going to be the last point, and set that equal to, say, null. Ooh, can't do that because we can make this nullable. Huzzah! Cool. So we have a nullable last point. If it's null, we're not going to add the point. But as long as we have the next one, we will add the point between the two of them and then lerp. So this becomes for each, that's not how you spell each, for each point in our points, if last point is equal to null, so if it doesn't exist yet, if it's the first element effectively, we're going to take the last point and say it equals our point. So last point equals the point, that will grab it, and then we want to continue, so we'll just break out. Otherwise, if that's not the case, we're going to stick this in an else, mostly just so if this continue ever goes away, we don't end up in trouble that we can avoid by just adding an else. I don't know if that, it won't have any effect yet, but if we maintain it or something, it could. So that's that. Then what we're going to do is take the last point and the current point. I'm actually going to set the last point here as well, just so that's going to be the last step, is just setting the current point to the last point. But then what we want to do is actually add a subpoint, which is going to be just vector3.lerp between the last point and the point with a ratio. The ratio is always going to be constant, so it's just going to be constantly taking that ratio and getting subpoints between everything. This should be fine, I hope. And we want to do last point.value. So we're going to actually swap this out and say if the last point has a value, if it doesn't have a value, then we want to do this part. If it does, take that value and do this. And then once we get to the end, just grab the point. And actually, I think we're done. I'm going to comment this out because this isn't going to work. We might be able to get that to work. But this actually, assuming I did all of this right, which is a big if, everything should work. We need to pass in the points. So the points are going to be our points, which means this becomes points. So we're actually dropping our initial transform bit where we had each point specified individually. Now you can have infinite number, and theoretically it should all still work. Don't really know if this is actually going to work because I don't really know, but we'll see. Can't convert the transform to the vectors. So what we need to do is actually get the position for each of those points, which we can do like this. This is going to select the position, so effectively transform the transform. That it's going to convert it. I think convert is a better word to use in this case, but it's going to convert the transform from Unity and just take the position out and actually pass that in. So this is converting that transform list into a list of just those positions for the points. And I think that makes a little bit more sense. Then we get here. And at the end, if we got to the end of this, we want to return the calculate Bezier point of our ratio and our subpoints. And that completes the recursion. Everything else should be good. Just to avoid some unfortunate errors, we're going to add a quick test here. If the points.length is less than or equal to 0, our current solution is actually going to work even if the points are 1. It will just return that point for every indice, which is going to be a total waste of resources, but that We're going to say that's on whoever's coding this. Don't just give it 1 point. But it makes it super easy for us because this way, if the points.length is less than or equal to 0, then we can do I think we'll just return for now. Theoretically, this is not the best idea. Let's do this a little bit better. Let's set the points to 0 and the positions to just a new vector 3 of the 0 vector, which we can actually use the included one, vector 3.0. And that's going to need to be in an array. Vector 3, blah. That. So what we're doing here is actually just effectively eliminating the line renderer if there's no points available. Because this runs on the editor, you could be editing this and take it to like 0 points just because you're editing it and maybe delete them or whatever, type something wrong. We don't want that to throw errors, so this should cover that. We'll see if it does. But this line should go away because we lost all of that data. So once we're going to have to reset this up for our 4 points, and hopefully it still works. Compiling, that takes a while apparently. I have no idea why. So I know I say that a lot, but it never used to take this long. And all of the things that would normally be the cause of slow compilation, like full disks or a CPU that's doing way too much, I've tested that. It's not the case. So I don't know what's going on. Maybe it's because, so this is the scene we used for our recording video. So we did a video on recording Unity. So actually taking the Unity frame recorder and recording video out of a Unity scene and using that. I'm still using that scene, and that has both our volumetric light and archimatics lighthouses in it. And maybe that's what's slow? I'm not entirely sure, but object renderer not set to an instance of an object. I suspect so that if points is null or the points length is whatever, so this will short circuit. So if it is null, it's not going to evaluate this, and if it isn't null, then it's going to evaluate this and say, does it have 0 elements as well? So that should catch that case. Apparently Unity uses null instead of a 0 array. I don't think I like that. But we will do, say, 4 points. And those aren't set up at all, so null references are happening all over the place. We should probably fix that. It works. Huzzah, it worked. Z sorting's totally broke. But that's kind of expected. I think I'm using a transparent material, which is why it's broke. But yeah, Z sorting is totally broken, but it totally worked. Oh, that's so cool. Cool. Yeah, so now we can render fancy Bezier curves, doing whatever we want. Let's add another point. So if I do, say, 5 now, and just attach it like that, what does this do? Oh, that's so cool. Okay, we are going to have so much fun with this. I am going to leave this here. I think this is a great place to get to. It looks super cool. I'm really excited. This is going to be fun. But this kind of, I think, shows it a little bit better how this whole thing is working. it's literally just a bunch of lerps. It's just lerping everything towards it. If you're unfamiliar with it, check out the first Bezier curve video we did. That kind of talks through a little bit more about how the original one is going. You can just expand that up to n. You can make that as many elements long as you want, and then you just reduce it down to that one point, and you just solve that. So this is cool. This means we can draw all sorts of funny lines, and it just works. So yeah, I will be putting this code out on GitHub so you guys can grab it and do whatever you want with it. Don't know why it just selected that, but anyway, you can grab the code, put it in your projects, do whatever, update it. I do accept pull requests if that's something that you want to update or something like that. Maybe fix this if I don't get to it. But other than that, if there's any suggestions you have or feedback for the channel, I'd love to hear it. The comments section is a great place to put that, or join the Discord and start chatting with myself and a few of the other people who are there. We like chatting about all sorts of things, like random projects you're working on, or just any issues you're running into and you want to talk them through with somebody. So that's an option. Would recommend. Other than that, thanks for watching, and I will see you guys in the next video. So till then, see you, Internet.